Good morning, and we're going to be going over a new topic, just like old topic. We used to talk about inertia as something's resistance to changing its velocity, and now we're going to be talking about rotational inertia, or sometimes this can be called moment of inertia. All right, but the rotational inertia right here, the variable we use to represent it is the capital I. So that's kind of intuitive, which is nice. And it is something's resistance to the change in rotational velocity. Okay, so regular inertia is how much it doesn't want to move linearly. Rotational inertia is how much it doesn't want to move rotationally. Okay, the two things that make it up is the mass and the how far the mass is distributed from where it's rotating. So for example, if you take something like this and I spin it on its axis, right? If I make this point the axis of rotation, now I don't have much of this meter stick's mass. In fact, only half of its mass goes out away from where the axis of rotation is, right? If I go all the way here and I make this the axis of rotation, and now I have this whole meter stick's mass out away, now this is going to be a lot harder to turn. It has more rotational inertia. Okay, so yeah, it's those two things, right? I can make this harder to turn by either making this meter stick more massive, giving it more mass, or by lengthening how far away that mass goes from the axis of rotation. I can't see my camera right now, so hopefully I was actually on the camera there. But like I said, this is also called a moment of inertia. Nobody really likes that name because it's not intuitive at all. Nobody really knows what a moment is. So rotational inertia is generally how we will describe this. And then units, remember they have to do with mass and the distance that mass is. So a kilogram and a meter squared. Okay, so if you think about this, that means that the equation for rotational inertia is most likely mass and then the distance squared, right? So the kind of like common things for this, and this is just a table of common moments or rotational inertias. You definitely don't have to memorize this at all, right? We're just going to use this to look at. But you can see this is a cylinder and it's solid, right? So 1/2 mass distance squared. So that's for like any radius, any mass, all that. But rather than just, getting stuck on what the formula is, I want you to compare it. So this is a hoop. It is the same mass, m, but now instead of that mass being evenly distributed like it is here, all the way from this axis of rotation and it's spread out, all of this hoop's mass is far away, right? So this thing is actually going to have a greater moment of inertia. All right, just got interrupted there, but we were talking about, so all of this thing's mass is a distance r from the center. So all of its mass is distributed further away, so it's going to have a greater moment of inertia, or rotational inertia. And you can tell that here. So this is 1/2 mr squared. This is just 1 mr squared. This has a greater moment of inertia. I keep saying that. Rotational inertia. Okay. You can tell that with the spheres too. Solid sphere, 2/5 mr squared. Hollow sphere, so all of this sphere's mass is now distributed out in that shell, 2/3. And 2/3 is a greater number than 2/5, right? This 2/5 would be 0.4, 2/3 would be 0.67, right? So this is a greater rotational inertia than the solid one. Even though they're the exact same radius, right, this thing has more mass further away from the center. So we're going to see this in action by taking a look at some of these problems. The way Khan will ask us, and we're not going to need to know formulas, we're not going to need to know anything like that. What we are going to need to know is how much mass something has affects its rotational inertia, and where that mass is affects rotational inertia, all right? So Ed spins a ball in a horizontal circle on a massless string. Danny has a similar ball, but wants to spin his slower. What could Danny do to make it harder to spin the mass from rest? So I have the dog right here covering up the answer choices because we want to make some predictions first. What could Danny do to make it harder? Well, making it harder means increasing the rotational inertia, right? So if rotational inertia is affected by mass or the distance that mass is distributed, then those are the two things that we could do. We could either add mass, okay, but that's probably not going to be the case because it says he has a similar ball. So usually that means all the qualities are staying about the same, right? So we could either increase the mass of the ball, or we could increase the distance from the axis of rotation that mass is located. So let's take a look and see what these are. Spin the ball closer to the ground. No, I don't know what that means. Use a heavier ball. Yep. Use a lighter ball. Nope. Make the string shorter, which would decrease the distance the mass is. Nope. Right? So definitely use a heavier ball. We are increasing the mass, which means we are increasing the rotational inertia. All right? Let's take a look at another one. Matt has a solid cylinder and a hollow cylinder and wants to spin each around the same axis of rotation. They have the same mass and radius. Which one has more rotational inertia? So we got to think about what are these two objects. One is solid. So this thing has the whole mass filled in, right? All of that mass is spread evenly throughout it. The other is a hoop, or sorry, what do they call it? A hollow cylinder. I don't really know how to draw a hollow cylinder, but all of this thing's mass is now only at the very edge where the hoop is, and this is just like this one, right? The hollow cylinder is going to be the one that has a greater moment of inertia or rotational inertia because the hollow cylinder has all of its mass distributed further away from the axis of rotation. So let's see. Which one has more? It's going to be the hollow one. Okay. And you'll see with really any shape, if they have the same mass and one is solid and one is hollow, the hollow one is always going to have more rotational inertia. Okay. All right, let's see. April spins a ball in a horizontal circle on a massless string. Yuki has a similar ball but wants hers to spin faster. So I'm thinking something spinning faster means that we're going to decrease the rotational inertia, right? It's going to have less resistance to changing its velocity, so it's going to go faster. So what could we do? Well, we could decrease the mass of the ball, or we could decrease the distance that mass is distributed, like the distance that mass is from the axis of rotation. So let's see. Spin the ball on the moon, make the string longer. This would increase R, right? So that wouldn't do it. Make the string shorter. This would decrease the radius. So I'm thinking C right now. Use a heavier ball. Definitely not. Definitely not. Definitely not. Boom. Right? It makes that distance shorter, which means we are decreasing the moment of inertia or the rotational inertia. And it's going to spin faster. All right? So a couple things with... we'll talk about that later. All right? Ladies and gentlemen, that is rotational inertia. Nothing too crazy.